Hello everyone. So we have reached last hour of rotational motion. This is the fifth hour and in this hour we are going to talk about rolling. This is a simple topic. It's just that you need to know what is transitional, what is rotational and how to combine them. So without wasting time, let's start learning the combination motion which leads us to rolling. So first of all, what is the meaning of combination motion? When a body performs both translational motion as well as rotational motion. When at any given instant the center of mass has a velocity as well as the body has an omega about the center of mass. So let's assume we have a rigid body and this rigid body has got its center of mass. Now, let's say the center of mass moves with some velocity. You will say the velocity possessed by the center of mass of the rigid body is the translational velocity. Remember that center of mass is the representative point to understand the translational motion of the body. Now let's say in addition to this velocity of center of mass, the translational velocity, we also have an omega. Now, how will you write the velocity of a point on the body? How will you write the acceleration of a point on the body? And how will you write the kinetic energy of this body? These are the three things we are going to discuss in this particular hour. So let's say there is a random point on this body and that random point is named P. Such that the position vector of this point P with respect to center of mass is given by R. Question is, how will you write the velocity of this point P? You will say this point P will have velocity because of both translational motion as well as the rotational motion. In circular motion, we have learned that if the particle has got angular velocity omega and its position vector is r, then the speed of circular motion comes out to be omega cross r. Understand the combination motion to be combination of translational and rotational. So you will say the velocity of point P on the body will be equal to the sum of its translational velocity and rotational velocity. Do remember that velocity is a vector quantity. So when you are finding the net velocity of point P and you add up the translational and rotational velocity, they must be added up vectorially, keeping direction into mind. So you will say the translational velocity will be same as the velocity of center of mass. And the rotational velocity due to the rotational motion will be omega cross r. So you will say the net velocity of point P will be Vcm plus omega cross r. Velocity of center of mass plus omega cross r. This will be the net velocity of the point P. Now in some other question, if you need to find, let's say, acceleration of point P, then how will you write the acceleration of point P? You will say, sir, same way. I will say the acceleration of point P has to be acceleration due to the translational motion plus the acceleration due to the rotational motion. So you will say acceleration of point P equals to acceleration due to translational motion plus acceleration due to rotational motion. Here is a catch. When a body performs pure rotational motion, for the sake of simplicity, I am calling it circular motion. When a body performs circular motion, it has got two types of acceleration. If the speed is changing, there is a tangential acceleration. And irrespective of which type of circular motion it is, uniform or non-uniform, there has to be an acceleration towards the center. That will be the centripetal acceleration. So we say that the acceleration of a particle P on this rigid body has got net acceleration equal to the sum of translational acceleration and rotational acceleration, and you must add these two accelerations vectorially. Now we can say that if we think of the rotational acceleration, again we have to take care of two types of acceleration. That will be the acceleration due to the centripetal acceleration and second the tangential acceleration. So we can further write the acceleration of point P to be acceleration translational plus acceleration tangential plus acceleration centripetal, because the resultant of these two acceleration will be the rotational acceleration. For the NEET preparation, do not need to worry, they won't ask you this particular thing. But what they are surely going to ask is how to write the kinetic energy of a body doing combination motion, and this part is really important. So to write the kinetic energy of a body doing combination motion, we have learned that when a body of mass m does pure translatory motion with a speed v, we write the kinetic energy simply as half mv square. And we have learned that when a body performs pure rotational motion about an axis, we write the kinetic energy as half I omega square. Then how will you write the kinetic energy of a body doing combination motion? So you will say the kinetic energy total equals to kinetic energy due to translation plus the kinetic energy due to rotation. Remember that kinetic energy is not at all a vector quantity, it's a scalar. Moreover, kinetic energy of a body can't be negative. Kinetic energy has to be positive. The change in kinetic energy can be negative. If the kinetic energy decreases, we say that the change in kinetic energy is negative. But beta, in general, kinetic energy of any body has to be positive. So you will say kinetic energy translational will be given by half into mass of the body into velocity of center of mass whole square plus kinetic energy rotational. Here in combination motion we say that assume that the center of mass does translational motion and the whole body rotates about the center of mass. So the second term will be the kinetic energy of rotational will be half into moment of inertia about the center of mass into angular velocity whole square. So we will write the total kinetic energy to be half mvcm square, that is the transitional part, plus half ICM omega square. Remember that here you must write the moment of inertia about an axis passing through the center of mass. Easy thing, and this part is the most important part. But first we will focus on the velocity part. So let's see one case. How to write the velocity in combination motion. Let's say we have this circular object which has got a translational velocity v and it has got an angular velocity omega. So the center of mass moves with a velocity v and this body also have an angular velocity omega. And let's say there are 4 points on the body A, B, C and D. How will you write the net velocity of any point on this body? So I have just told you, if a body performs combination motion, find the velocity of every point on the body due to translational. Then find the velocity of every point on the body due to rotational, and the net velocity has to be the vectorial sum of both translational and rotational velocity. For a matter of second, visualize that this body does not have any omega. This body is performing pure translational motion. Then each and every point on the body, whether A, B, C or D, if it performs pure translational motion, all the points A, B, C, D will have the same velocity. Now beta, for another second, forget that this body has got any translational velocity. Visualize that this body does only pure rotational motion. So if this body has got no translational velocity and it performs pure rotational motion with an angular velocity omega, then the velocity of point A will be tangentially, right? How much? Omega r towards right. The velocity of point V will be again tangentially, where? Downward. How much? Omega r downward. The velocity of point C will be backward. How much? Omega r backwards. And the velocity of point D will be upwards. Omega r upwards. So now what you have to think is that, okay, if the body would have done pure translational motion, the velocities would have looked like this. If the body would have done pure rotational motion, the velocities would have looked like this. If the body is doing combination motion, then the net velocity of any point on the body will be the vector sum of translational velocity and rotational velocity. So let's start visualizing one by one. So think of the body. The center of mass has a velocity. Let's first visualize the point A. The point A will have translational velocity v towards right, as well as because of the rotational it will have a velocity omega r also in the same direction. Beta, here I do know that v and omega are vectors. They are the velocity vectors, velocity due to translational and velocity due to rotational. And the net velocity, since both the vectors are in same direction, will be v plus omega r. Now let's visualize the point B. The point B, the frontmost point. Because of translational, it will have velocity v towards right. Because of rotational, it will have a tangential velocity omega r downward. So the net velocity will be the vector sum of these two velocity, and the vector sum of these two velocity of v and omega r, which are in perpendicular direction, will be under root of v square plus omega square r square. Now let's talk about the lowest point, the point C. At point C, because of translational, velocity will be v towards right. Because of rotational, velocity will be omega r backwards. So you will say at point C, because of translational, v towards right. Because of rotational, omega r towards backward. And at the point D, because of translational, v towards right. And because of rotational, omega r upwards. So these are the velocities. Now, how to write the net velocity at point A, B, C, D? Sir, it's very easy. At point A, the topmost point, the net velocity will be V plus omega r. At point B, the frontmost point, the net velocity will be the vector sum of the translational velocity V and the rotational velocity omega r. So that will be under root of V square plus omega r whole square. So that will be under root of V square plus omega square r square. Now let's think of the lowest point. At the lowest point, there can be two cases. If beta V is greater than omega r, then at the lowest point, the net velocity will be towards right. And that net velocity will be V minus omega r. Think of another case. If omega r is greater than V, if omega r, rotational velocity, is greater than translational, if omega r is greater than V, then at the lowest point, the net velocity will be towards left. That will be omega r minus V. So at the lowest point, the velocity will be V minus omega r towards right. When I have written V minus omega r, in my heart I have assumed that V is more than omega r. V is more than omega r. So the net velocity towards right comes out to be V minus omega r. The last one, the point D, again one velocity V here, one velocity omega r here. The vector sum will be under root of V square plus omega square r square at some angle. Okay. So now let's move on further and discuss more about velocity in case of combination motion. So let's do a problem and then we will move on to the condition of pure rolling. So the question goes like this. There is a plank which goes towards right with a speed of 5 meter per second, and on the plank there is a circular object, can be disc, ring, solid sphere, hollow sphere, anything, and the translational velocity of this circular object is 2 meter per second towards right. The radius of the circular object is 1 meter. Question is, if no relative motion between the cylinder and the plank, if there is no relative motion between the cylinder and the plank at the point of contact, find the angular velocity of the cylinder. So when they say there is no relative motion between the cylinder and the plank at the point of contact, it means that at the point of contact, both the cylinder and the plank have the same velocity. We know that the velocity of the plank at the point of contact is 5 meter per second. So the velocity of cylinder as well at the point of contact should be 5 meter per second. And they are asking me determine the angular velocity of the cylinder. So let's assume that the cylinder has some angular velocity omega. So at the point of contact, the speed of plank is 5 meter per second. At the point of contact, the speed of plank is 5 meter per second. So the cylinder must also have the same speed of 5 meter per second towards right at the point of contact. If the cylinder or the circular object does combination motion, different points will have different velocities, right? Both in magnitude and direction. So you will say, assume cylinder to have an angular velocity omega. So let's assume this cylinder has an angular velocity omega towards left. Now question is, what will be the velocity at the point of contact for this cylinder? So you'll say, sir, it's easy. You have to write velocity due to both translational and rotational. So because of translational, at this point of contact, it will have velocity of 2 meter per second towards right. If I have assumed an angular velocity omega and the radius is 1 meter, so at the point of contact, because of rotational, there will be a velocity tangentially that will be omega into 1. So there will be a rotational velocity as well, omega into 1, that will be omega. So the net velocity at point of contact will be 2 plus omega. So you will say because of translational, velocity at point of contact will be 2. If you have assumed that angular velocity is omega, then because of angular velocity omega at point of contact, the velocity will be omega into r, and r is 1, so you get omega. So you will say the net velocity at point of contact will be 2 plus omega. And for no relative motion at point of contact, this 2 plus omega should be equals to 5. For no relative motion, 2 plus omega has to be equals to 5, and beta omega comes out to be 3 radian per second. The common doubt which students have and on which students waste a lot of time is that, sir, how come you assumed omega to be anti-clockwise? This can be one of the other reason of why you don't solve question of physics quicker. The students waste a lot of time thinking that I should take omega this way or that way or what to do. Better do not waste so much of time. Assume omega in one sense. If actually the omega will be in that sense, your answer will come out to be positive. If I would have solved the same question taking here angular velocity clockwise, then beta I would have got a negative answer. And that negative will tell me that the direction I have chosen for omega is wrong. I should choose it the other way around. Okay, so don't waste so much of time on deciding in which sense I should take the omega. So let's now learn the condition of pure rolling. So let's say we have this circular object, can be ring, disc, solid sphere, hollow sphere, anything, which has got a translational velocity v, a rotational velocity omega, and a radius r. What is the meaning of pure rolling condition? It means that no relative motion at the point of contact. It means that no relative motion at the point of contact. Now, since this body is moving on a fixed surface, at the point of contact, the velocity of this fixed surface is zero. This means that even the velocity of this rolling object at the point of contact should be zero. And we have learned that if a body has translational velocity v, angular velocity omega, and a radius r, then what does the velocity look like at different point? At the topmost point, velocity is v plus omega. At the frontmost point, under root of v square plus omega square r square. At the lowest most point, if v is assumed to be greater than omega r, the net velocity comes out to be v minus omega r towards right. What are we learning? Sir, the condition of pure rolling. What is pure rolling? When there is no relative motion at the point of contact. We know that this surface is fixed. So the velocity of surface at the point of contact has to be zero. So for pure rolling, even the lowest point on this circular body at the point of contact should have zero velocity. For this point to have zero velocity, v minus omega r should be equals to zero. And when I say that v minus omega r has to be zero, it means that I am saying for pure rolling on a fixed surface, v should be equals to omega r, and this is the condition. For pure rolling on a fixed surface, v should be equal to omega r. So for no relative motion at point of contact, we know that these two velocities, the translational velocity and the rotational velocity omega r, should cancel out if the body performs pure rolling on a fixed surface. And for such a condition, v has to be equals to omega r. Okay. Now, if a body performs pure rolling, then what is the velocity of different points on the body? So we have just learned the condition for pure rolling on a fixed surface is that v has to be equals to omega r. So then what will be the velocity of the topmost point? So you have learned that velocity of topmost point is v plus omega r. And since for pure rolling omega r equals to v, so if a circular object performs pure rolling on a fixed surface, then the topmost point will have velocity v plus v, because omega r equals to v. So the velocity of topmost point will be 2v. What will be the velocity of this frontmost point? For pure rolling, omega r equals to v. So here in place of omega r, beta substitute v. So you get under root of v square plus v square. That becomes root 2v square. That is nothing but root 2v. So the velocity of the frontmost point will be root 2v. Similarly, in case of pure rolling, what has to be the velocity of lowermost point? Sir, there has to be no relative motion at the point of contact. The lower surface is fixed. So this body at the point of contact should have zero velocity. And similarly, the last point D will have here velocity v and upward velocity omega r, which will also be equals to v. So the net velocity will be root 2v. Okay. Let's continue ahead. So question is, which half of a circular body doing pure rolling has higher kinetic energy? So there is a circular body doing pure rolling on a fixed surface, pure rolling on a fixed surface. Which half of this circular body has higher kinetic energy, the upper half or the lower half? So we have just learned that if we have got this circular body which does pure rolling and the center moves with a velocity v, then the velocity of topmost point is beta 2v. The velocity of lowest most point is 0. Since the topmost point moves faster, the upper half particles have a higher speed compared to lower half particles. Since the upper half particles have higher speed compared to lower half particles, the upper half of such a body performing pure rolling will have more kinetic energy associated with it compared to the lower half. So in the upper half, the speed is greater. So the upper half has greater kinetic energy compared to the lower half. Now let's move on further and understand more concepts. So this, I will say, is one of the most important question in rolling. So pay close attention to what we are doing here. Question is, there is a circular body It can be ring, disc, solid sphere, hollow sphere, can be anything. There is a circular body. And we are applying a force F at a height h above the center of mass of the circular body. Question is, at what height above the center the force must be applied on the circular body, can be ring, disc, anything, of mass m, radius r and radius of gyration k, so that it starts pure rolling on frictionless surface. So here we have a frictionless surface. At what height above the center of mass we should apply a force so that this body starts pure rolling? We have just learned what is the condition of pure rolling. We have learned that if a body performs pure rolling on a fixed surface, then its translational velocity v and the rotational angular velocity omega should be correlated as v equals to omega r. If we differentiate both the side with respect to time, we get dv by dt, which is equals to a, equals to d omega by dt, which is equals to alpha into r. So for pure rolling on a fixed surface, if the body is moving with a constant velocity, then the condition is v should be equals to omega r. And if the body is also accelerating, then the acceleration of the center of mass should be equals to angular acceleration of the body about center of mass into r. A has to be equals to alpha. Now you want this body to perform pure rolling on a frictionless surface. So there is only one force, this and this force only, which will provide it acceleration, as well as this force will be the only force providing a torque about the center to provide it angular acceleration. So this force provides it translational acceleration, as well as this force provides the torque that provides its angular acceleration. So you will say, think of the forces acting. So there is only one force F in the horizontal direction. Let's say the body gets an acceleration A, and because of the torque produced by this force, the body gets an angular acceleration alpha. So from the force equation, we can say that F equals to mn, and from the torque equation, we can say the torque about the center F into h has to be equals to moment of inertia of the body about an axis passing through center of mass into alpha. So you can make these two equations. Now you know that for pure rolling, the condition is that A has to be equals to alpha r. For no slipping, A has to be equals to alpha r. So if you substitute the value of A here or the value of alpha here and solve, you can find out at what height you should apply the force. So you can rewrite these two equations as F equals to mn, yes, F into h equals to I. In place of alpha, I am substituting A by r in the second equation. Now better divide the equations both the side. So on the left hand side, F get cancelled, okay, and on the right hand side, A get cancelled. So what you get is 1 by h equals to m upon I by r, and the r moves from denominator of denominator to the numerator. So you get 1 by h equals to m r by I. So you can write 1 by h equals to m r by I, or you can flip it both the side and write h equals to I by mr. H equals to I by mr. This body has got a radius of gyration k about its axis. So in place of moment of inertia, you can write mk square. So let us see here, h equals to mk square by mr. Cancel out m and m. So h comes out to be k square by r. Multiply both numerator and denominator with r. So what you get here is h equals to k square by r square into r. So h comes out to be mk square by mr, that can be written as mk square by mr square into r, that can be written as k square by r square into r. And this is an important result, you should keep it in mind. In a little while, I will make you remember the value of k square by r square for all different type of objects. So what I want from you is to remember this particular result, that if you want a body to start doing pure rolling on a frictionless surface, then the force must be applied at a height equals to k square by r square into r. So before we utilize this result and understand what is the value of k square by r square for different bodies, let's first do some questions to understand how to solve these type of questions of pure rolling. So the next question is, determine the friction force that acts on the disc. So this circular object they have mentioned, this is a disc. If the disc performs pure rolling, So here we have a disk and we have applied a force at the center of disk. Since we have applied a force passing through the center of mass of disk, this force do not provide any torque, right? And if we want this disk to do pure rolling, it should have both acceleration as well as angular acceleration, and the relationship between them should be that A equals to alpha r. So this force will only provide acceleration. To provide angular acceleration, some friction force should act. Let's assume a friction force equals to F, small f, acts on it. So assuming the friction force acting to be F, and visualize the forces. So there is external force F, there is friction force small f, and under the influence of these two forces, the body moves with an acceleration A and an angular acceleration alpha. From the force equation, you can write the net force in direction of acceleration equals to mass into acceleration. While teaching you center of mass, I told you all the forces acting on the body can be assumed to be acting at the center of mass to determine the acceleration of center of mass. Here the acceleration of center of mass is A. So you can visualize this force F acts at the center of mass as well as the friction force acts at the center of mass. So F minus F. For force equation, we can write F minus F, the net force in direction of acceleration equals to mass into acceleration. Now let's make the torque equation. What is the torque about the center of mass because of this force? So you will say, sir, there is no torque because of this force. Why? Sir, this force passes through the center of mass, so R is 0, hence the torque is 0. Okay. So who provides the torque to provide this angular acceleration alpha? Sir, friction. The friction force acts at a perpendicular distance R. So the torque provided by a friction force is Fr, and this torque will be equals to I into alpha. Now since we have a disk, the moment of inertia about an axis passing through the center of mass and perpendicular to the disk will be mr square by 2. So we can write the torque equation, the net external torque Fr, because only friction provides the torque, equals to I, which is mr square by 2 into alpha. And then we will make one more equation, that is a standard equation that always have to be made. That will be the equation of no slipping, the condition of pure rolling. If the body performs pure rolling on this fixed surface, then V equals to omega r. Since V equals to omega r, you can say dV by dt equals to d omega by dt into r. So you can write A equals to alpha r. So for pure rolling, acceleration has to be equals to alpha r. So beta, that will be the third equation. So for no slipping, A equals to alpha r. So now we can solve these three equations. From the last equation, we know that alpha equals to A by r. Substitute it here. So you get Fr equals to mr square by 2 into A by r. Beta, cancel out one r with one r, another r with another r. So you get F equals to ma by 2. Now we need to find friction force. So we need to eliminate ma. So we know that ma can be written as 2f and substitute it here. Once you substitute, you get F minus F equals to 2f, or force equals to 3f, or the friction force has to be equals to F by 3. Hence, on solving, we get the friction force equals to F by 3. But one thing here. Here we got plus F by 3. Not minus F by 3. Since we got plus F by 3, it means that the direction we have chosen for the friction force is right. In this case, the friction force will act in backward direction and it will have the magnitude 1/3 of the applied force. Let's practice one more question of same type to understand. So question is, determine the friction force acting on the solid sphere. This is a solid sphere, okay? For solid sphere, moment of inertia is 2 by 5 mr square. Determine the friction force acting on a solid sphere if the solid sphere performs pure rolling. So how much friction force must act on this solid sphere given that this solid sphere performs pure rolling? So let's assume that a friction force F acts. So if a friction force F acts backward and under the influence of friction force and external force, this whole solid sphere performs pure rolling having an acceleration A and angular acceleration alpha. From the force equation, we can write beta F minus F equals to mass into acceleration. From the torque equation now, focus. Last time the force was passing through the center. So its torque about the center of mass was 0. But this time the force has been applied at the highest most point. So here both the forces will provide torque. First of all, in which sense will be the torque because of external force? So sir, just visualize the hinge, the center of mass, the external force, and this is trying to turn it clockwise. Now, in which sense the friction is providing the torque? So, sir, just think of the center of mass as if the body is hinged at the center of mass, and the friction force. In which sense this friction force provides torque? Clockwise. So, both the external force as well as friction force are providing torque in the clockwise sense. The torque because of external force will be F into R. The torque because of friction force will be F into R. So the net torque, as both of them are trying to turn it clockwise, will be equals to Fr plus small fr. So from torque equation, capital Fr plus small fr equals to I into alpha, and the moment of inertia of solid sphere is 2 by 5 mr square into alpha. Now the same old equation, third equation. For the condition of no slipping, A has to be equals to alpha r. Now beta, we can solve these three equations to find out the friction force. How? Since you know that A equals to alpha r, alpha has to be equals to A by r. Here in place of alpha beta, substitute A by r. Once you have substituted, cancel out 1 r with 1 r here and 1 r with 1 r here. So you get an equation F plus F equals to 2 by 5 ma. And from the first equation, you know F minus F equals to ma. Your mission is to find the friction force. So you need to eliminate ma. Substitute the value of ma from first equation into second equation. So you will get F plus F equals to 2 by 5 times F minus F. In place of ma, from the first equation, I have written F minus F. So you get 5F plus 5 times the friction force equals to 2 times external force minus 2 times the friction force. Bring the term of friction force on one side. So on the left hand side you get 7F. Bring this 5F to right hand side equals to minus 3F. So the friction force comes out to be minus 3F by 7. Okay, so on solving, the friction force comes out to be minus 3F by 7. Once you got that friction force is minus 3F by 7, what does the minus sign here tells you? It tells you, bhai, you have taken the wrong direction. You have assumed the friction to be in backward direction, but since the friction force came out to be negative, it must be in the forward direction. So, hence the negative sign tells us that we have chosen the wrong direction of friction force. In this particular case, the friction force must have acted in the forward direction. So now getting back to the same thing, that at what height above the center we should apply a force so that the body performs pure rolling. There we got that the height at which the force should be applied on a frictionless surface is k square by r square into r. So we need to understand what is k square by r square. So the next heading, what is k square by r square for different types of body. We know that for any object I equals to mk square. So if we first think of ring or hollow cylinder, as both of them have got moment of inertia mr square about their axis, I can write for ring or hollow cylinder I equals to mr square. And we know that moment of inertia can also be written as mk square. So mk square equals to mr square. So from here you will cancel out m and you will get the value of k square by r square equals to 1. So the ratio k square by r square for ring and hollow cylinder comes out to be equals to 1. Similarly, if you have a disc or solid cylinder, about their axis, both disc as well as solid cylinder have the moment of inertia of mr square by 2. That's why they are being talked about together. So you will say I equals to mr square by 2. So mk square equals to mr square by 2. So beta, what will be the value of k square by r square? So cancel out m and m. So you get k square upon r square equals to half. So for disc and for solid cylinder, the value of k square by r square is half. Now the next one, our hollow sphere. We know that moment of inertia of a hollow sphere is 2 by 3 mr square. So mk square equals to 2 by 3 mr square. Cancel out m, so you get k square by r square equals to 2 by 3. And for a solid sphere, I equals to 2 by 5 mr square. So mk square equals to 2 by 5 mr square. So let cancel out m and m. The k square by r square comes out to be 2 by 5. So it is an easy thing to remember. For disc and for solid cylinder, moment of inertia is half m r square. So that half is k square by r square. For hollow cylinder, moment of inertia is 2 by 3 m r square. So that 2 by 3 is the ratio of k square by r square. For solid cylinder, the moment of inertia is 2 by 5 m r square. So that 2 by 5 before m r square is the ratio of k square by r square. So it is an easy thing to remember. And as for ring and hollow cylinder, we get moment of inertia as mr square. That one before mr square is the ratio of k square by r square. So now let's compare the value of k square by r square for different bodies. For the ring, it is 1. For the disc, it is half, which is same as 0.5. For the hollow sphere, it is 2 by 3, and 2 by 3 is 0.66666, never ending. And for solid sphere, it is 2 by 5, that is 0.4. Now here tell me, whose value of k square by r square is highest? So you will say, sir, the k square by r square is highest for ring, second for hollow sphere, third position for disk or solid cylinder, and at fourth position for solid sphere. So solid sphere has the lowest value of k square by r square, while ring or hollow cylinder has the highest possible value of k square by r square. So the value of k square by r square for ring is greater than hollow sphere 0.66, is greater than for disk or for solid cylinder 0.5, is greater than that for solid sphere, which is 0.4. So you need to remember this order as well, because many times question get asked from here. So moving on to what we were learning already. So height of force, at what height above the center a force should be applied so that the body performs pure rolling even on a frictionless surface, even on a smooth surface. To keep the body perform pure rolling on smooth surface, we have learned that the force must be applied at a height equals to k square by r square into r. We know that for ring and hollow cylinder, the value of k square by r square is 1. So h will be equals to 1 into r. So h will be equals to r. If beta h equals to r, it means that the force should act at the topmost point. So k square by r square is 1. So h equals to r. So in the case of ring or hollow cylinder, the force must be applied at the topmost point so as to make it roll on a frictionless surface. If you have disc or solid cylinder, then beta for disc or solid cylinder, the value of k square by r square is half. So h comes out to be equals to half into r, that is r by 2. This means that for the case of disc or solid cylinder, the force must be applied at a height equals to r by 2. So you have to apply the force at half the radius, at a height r by 2. If you have a hollow sphere, for hollow sphere the value of k square by r square is 2 by 3. So the force must be applied at a height 2 by 3 above the center so as to make it roll even on a frictionless surface. And the last one, for a solid sphere, the value of k square by r square is 2 by 5. So the force must be applied at a height equals to 2r by 5 so as to make it roll on a frictionless surface. Okay, remember these data points. So let's move on. A ring is provided with an angular velocity omega. A ring is provided with an angular velocity omega and gently placed on a rough surface. What will happen? So you took a ring, you just gave it omega, no transitional velocity. What will happen? So you will say, sir, at the point of contact, since the ring only has omega, at the point of contact, the ring will have velocity backwards. At the point of contact, since the ring will have a backward velocity omega r at this instant, tell me in which direction the friction force will act at the point of contact on the ring. So sir, since the ring has got a backward velocity omega r, a friction force will act forward. Yes. Now this friction force acting on the whole body in forward direction will start increasing its forward speed. And this friction, think over it, provides a clockwise torque or an anti-clockwise torque. So sir, think of the body, think of the center of mass, think of the friction force which is forward. So it provides an anti-clockwise torque. And actual omega is clockwise. And the friction provides anti-clockwise torque. So the torque provided by the friction force will reduce the omega. It will increase the velocity, it will reduce the omega, and it will keep on doing it till the time the body starts pure rolling. Once the value of V and omega sets such that V becomes equals to omega r, then at the point of contact, there will be no relative motion. And once there will be no relative motion, there will be no friction force. So remember this. At the point of contact, the point on the ring has backward velocity. Hence, the friction force will act in forward direction. This friction force acting on the ring in forward direction will provide an anti-clockwise torque and will increase its velocity in the forward direction. So this friction force will increase the velocity and will decrease the omega. It will keep on increasing the velocity and decreasing the omega till the time the body has such a velocity and such an omega such that V equals to omega dash into r. And once this is achieved, there will be no relative motion at the point of contact. And once there will be no relative motion at the point of contact, the friction force will cease to act. So you will say, this friction force will increase the velocity and decrease the omega till the time the velocity and angular velocity matches to make the ring undergo pure rolling. So the velocity will keep on increasing, omega will keep on decreasing, and the final destiny of this ring will be to do pure rolling on this rough surface. Sir, I haven't understood this example. Do not worry. There are two more examples of the same time, and I am trying to make a point here. So the next example is, now if a circular object is given velocity, no omega, velocity and placed on a rough surface, what will finally happen? So you have taken an object, just provided it velocity, no omega, and placed it on a rough surface. What will finally happen? So you will say, sir, this time you have just provided velocity. So at the point of contact, because of translational motion, it will have velocity towards right. So it will have friction force backwards. Now understand that when you are thinking of translation, forget rotation. So velocity forward, force backwards, so acceleration backwards, so the velocity will decrease. Okay. Now think using the rotational, and this force provides a torque in clockwise sense. So that clockwise torque will provide clockwise angular acceleration and hence will increase the clockwise omega. So this friction force is trying to decrease the velocity. It is trying to increase the omega. It will keep on decreasing the velocity. It will keep on increasing the omega till the time at any instant, let's say later, its speed is v dash and angular velocity is omega dash. Till the time it reaches such a condition that v dash equals to omega dash r. And once that happens, at the point of contact, the velocity will be zero and then the friction force ceases to act. So the velocity is forward, the friction force will be backward. Due to relative motion at the point of contact, the friction force acts backward. The friction force decreases the v because it is in direction opposite to the velocity. The friction force decreases the v and provides a torque which increases clockwise angular velocity. So the speed decreases, omega increases, and finally the body performs pure rolling. So what we have learned just now, if you take a circular body, just provided omega and place it on a rough surface, finally it will do pure rolling. If you provide it just velocity and place it on a rough surface, it will finally again do pure rolling. Sir, what if you provide both velocity and omega? That's the third case. So if now the body has been provided velocity as well as omega, if the body is provided both velocity and omega, but v is not equals to omega, it means that the body is not doing pure rolling. At the point of contact, the velocity is not zero. What will finally happen? Now here we have to consider two cases. The case number one, if v is greater than omega r. If v is greater than the angular velocity you have given right now into the radius. If the translational velocity you have given is more than omega r, then what happens? So if v is greater than omega r, then the net velocity at the point of contact will be towards right. Sir, how do you know? Arey beta, simple. Because of translational, v towards right. Because of rotational, omega r backwards. Since I am saying that I have assumed v to be greater than omega r, the net velocity at point of contact will be towards right, and that will be v minus omega. Since at the point of contact this circular body will have velocity towards right, the friction force will act backward. Now tell me, this friction force will do what to the velocity and omega? Sir, as v is more than omega r, and we have found that this friction force is such that it will try to decrease the velocity. And this friction force will provide a clockwise torque so as to increase the omega. As at this particular instant the velocity of body is greater than the angular velocity into radius, and the friction is such that it is decreasing the velocity and increasing the omega. It will keep on acting till the time v becomes equals to omega r, and once v becomes equals to omega r, at the point of contact there is no relative motion and then the friction force ceases to act. So in the first case, f decreases the velocity and increases the omega till the time pure rolling starts, and once the pure rolling starts, the friction force ceases to act. Let's think of second case. What if the angular velocity provided is very large? So omega r comes out to be more than v. If omega r is more than v, then at the point of contact, the backward velocity because of omega r will be more than the forward velocity because of transitional. So the net velocity at the point of contact will be backward omega r minus v, and the friction force is forward. Now think that the body has a velocity v and an angular velocity omega. What is this forward friction force trying to do? So this forward friction force is trying to increase the velocity, because velocity is forward, friction force came out to be forward, it is trying to increase the velocity. What is this forward friction force trying to do with the omega? Sir, this forward friction force provides an anti-clockwise torque, so it is trying to decrease the omega. Since in this case omega r was more than v, the friction force chose such a direction so as to increase v and to decrease omega till the time the velocity becomes equals to omega r. And once the velocity becomes equals to omega r, at the point of contact there is no relative motion and hence the friction ceases to act. So here the friction increases v and decreases omega till the time the rolling starts. So sir, what are you trying to say? You take a circular object, place it on a rough surface. Whether you give it velocity, it will ultimately do pure rolling. Whether you give it omega, it will ultimately do pure rolling. If you give certain velocity, certain omega, such that it is not doing pure rolling right now, the friction will act and after some time it will do pure rolling. So the ultimate destiny is that there will be no relative motion at the point of contact and friction will keep on acting till the time there is some relative motion at the point of contact, because friction opposes relative motion. So friction will keep on acting till the time there is some relative motion. So the ultimate destiny is that there will be no relative motion between the surfaces at the point of contact. Okay, moving on. Some important things that we should know about the rolling motion. If a body performs pure rolling such that v and omega are related as v equals to omega r, then we know at the lowest point speed is 0, at topmost point the speed is 2v. The path taken by one of the point on such a body, this shape is called the shape of cycloid. This shape is called the shape of cycloid. When the wheel turns once, the center moves forward by a distance 2 pi r. When the wheel turns once, the center moves a distance forward equal to 2 pi r. So a particular point moves on a curve called the cycloid. The length of the cycloid is nothing but 8 times the radius. The length of the cycloid is 8 times the radius. So if they ask, when a wheel performs pure rolling, what is the displacement of a point in one cycle? So you will say, sir, displacement, direct distance 2 pi r. What is the distance traveled by a point on the circumference of wheel in one cycle? What is the distance traveled by a point on the circumference of wheel in one cycle? You will say, sir, that distance is 8r. So the length of the cycloid is 8r and the displacement of one point on the cycloid is 2 pi r. Next thing, if the body has a mass m and center of mass moves with a speed v, then you can write the kinetic energy equals to kinetic energy translational plus kinetic energy rotational. This is really important part, focus. The kinetic energy translational will be half mv square and you can write kinetic energy rotational as half I omega square. But now we are going to do a special thing. For a body doing pure rolling, you can write v equals to omega r, yes. So you can write omega equals to v by r, yes. And for this body, in place of I, you can write mk square. So you can write the same kinetic energy as kinetic energy transitional half mv square plus kinetic energy rotational. In place of kinetic energy rotational for a body doing pure rolling on a fixed surface, in place of I wrote mk square, and in place of omega square I have written v square by r square. So beta, from the first two terms you can take half mv square common. Once you take half mv square common, what you are left with is 1 plus k square by r square. And now you have marked up the value of k square by r square for different type of body. So once more, focusing on kinetic energy because this is important. So for a body doing pure rolling on a fixed surface, kinetic energy translational equals to half mv square. The kinetic energy rotational is half I omega square, that can be written as half into mk square. In place of omega you can write v by r whole square, so that gives you half mv square into k square by r square, or k square by r square times half mv square. This is the kinetic energy rotational. And the kinetic energy total equals to, take half mv square common, so you get 1 plus k square by r square into half mv square. Now we have remembered what is the value of k square by r square for different type of bodies. For a ring and hollow cylinder, k square by r square is 1. For a disc and solid cylinder, k square by r square is half. For a hollow sphere, it is 2 by 3. For a solid sphere, it is 2 by 5. So if I tell you a ring is performing pure rolling on a fixed surface, Which kinetic energy will be more, translational or rotational? You will say, sir, for a ring, k square by r square will be 1. So for a ring, the rotational kinetic energy will also be half mv square. Translational will be half mv square, rotational will also be half mv square. So the total energy will be mv square. Similarly, for a disk, the rotational kinetic energy will be half of translational kinetic energy because k square by r square is half. For a hollow sphere, the rotational kinetic energy will be 2/3 of translational kinetic energy. For a solid sphere, the rotational kinetic energy will be 2/5 of translational kinetic energy. Right? So let's see one example. What fraction of kinetic energy of a solid sphere doing pure rolling on a horizontal surface is translational? So we know that if we have a solid sphere, the value of k square by r square for solid sphere is 2 by 5. We can say that the translational kinetic energy will be half mv square. For a body, a circular body doing pure rolling, the rotational kinetic energy will be k square by r square times half mv square. And the total kinetic energy, which will be the sum of translational plus rotational, will be 1 plus k square by r square into half mv square. So this will be the total kinetic energy. They are asking me what fraction of kinetic energy of a solid sphere doing pure rolling on a horizontal surface is translational. So what fraction of the total kinetic energy is translational? Total is 1 plus k square by r square times half mv square. Translational is half mv square. So what fraction is translational? So you will say the fraction of total kinetic energy that is translational is given by the translational kinetic energy upon the total. So that will give you beta half mv square upon 1 plus k square by r square times half mv square. You can cancel out this half mv square part. So what you get is 1 plus k square by r square. For a solid sphere, we will substitute the value of k square by r square as 2 by 5. So you get 1 upon 1 plus 2 by 5. That becomes 1 upon 7 by 5. That will be equals to 5 by 7. So for a solid sphere, you get 1 upon 1 plus 2 by 5. That will be equals to 1 upon 7 by 5. That will be 5 by 7. So 5 by 7 of the total kinetic energy is translational. Let's practice one more example of same type. What fraction of kinetic energy of a ring rolling on a horizontal surface is translational? What fraction of kinetic energy of a ring rolling on a horizontal surface is translational? So again you will say the same thing. Sir, the translational kinetic energy is half mv square. For a circular body doing pure rolling on a fixed surface, we say that the rotational kinetic energy is k square by r square times half mv square. So the total kinetic energy has to be equals to 1 plus k square by r square times half mv square. Now they are asking me what fraction of total kinetic energy is translational. So simply do translational by total. So fraction of kinetic energy that is translational is given by translational half mv square upon total, which is 1 plus k square by r square into half mv square. So you can cancel out half mv square, half mv square. So what you get is 1 upon 1 plus k square by r square. And for a ring, the value of k square by r square is 1. So we get this to be equals to 1 upon 1 plus 1. That becomes 1 by 2. So the fraction of total kinetic energy that is translational is nothing but half. So let's talk more. Question is, here we have an inclined surface. From the top of the inclined surface, we have released a circular object. It might be ring, disc, hollow cylinder, solid cylinder, anything. Question is, what will be the speed of this circular object when it reaches the base? But there is a twist in the question. A circular object is released from the top of an incline of height h. Determine the speed of the object on reaching the base given that case 1, the incline is frictionless. So the friction coefficient for the incline is 0. And second, friction is sufficient for the body to undergo pure rolling. If this incline is frictionless, then what will be the speed on reaching the base? And if friction is sufficient for body to undergo pure rolling, then what will be the speed on reaching the base? So if you think of the first case, when the surface is frictionless, so which forces will be acting on this circular body? So there will be a force of gravity downward, and there will be a force of normal, I'm talking about the first case when the inclined surface is frictionless. So the force of gravity passes through center of mass, force of normal passes through center of mass. So about the center of mass of this circular object, there will be no torque because of the force of gravity and the force of normal. Hence, this body won't roll at all. This body will simply slide down. It will only do translational motion and no rotational motion. Why? Because there is no force present to provide the torque. Once more, if the friction is absent, if it's a frictionless surface, then the forces acting on this circular object will be gravity and normal. Both of them passes through the center of mass, so they do not provide any torque. As they do not provide any torque, the body will do just pure translational motion. So for such a body, you will say the work done by gravity plus work done by normal equals to change in kinetic energy. Which type of kinetic energy? This body will gain only translational kinetic energy. So you will say, if the surface is frictionless, the body gains only translational kinetic energy. It does not rotate, it moves straight down. So you can write work done by all the forces. Now the work done by normal has to be 0. We have learned that the work done by normal of a fixed surface is 0. Only gravity will do the work, and that work will be mgh. So mgh, the work done by gravity, will be equals to change in kinetic energy. Final kinetic energy half mv square minus initial 0. So you can simply write mgh equals to half mv square, or from here cancelling out bringing this 2 up, taking the root, you can say v has to be equals to root 2gh. So this is the speed of this object on reaching the base given that the surface is frictionless. Now what will be the speed of this object on reaching the base given that there is friction on the surface? So if there is friction on the surface, then the friction will act in the upward direction, up on the incline. Now this friction will provide a torque about the center. Now as the circular object moves from top to the base, 3 forces will act on the body. So visualize an intermediate state. The 3 forces will be force of normal passing through center of mass, force of gravity passing through center of mass, and force of friction. Now tell me, out of these 3 forces, which force provides the torque? The friction. Because of that, the body rolls. Now second question is, what will be the work done by gravity as this body moves from top to bottom? So work done by gravity will still be mgh because the force is downward mg and the body moves down a height h, so the work done by gravity will be mgh. What will be the work done by normal? So the work done by normal of a fixed surface is 0, so the work done by normal will be 0. Can you tell me what will be the sign of work done by friction given that this body performs pure rolling as it moves down? What will be the sign of work done by friction if the body performs pure rolling as it moves down? Now majority of students will say that the work done by friction will be negative. Why? Displacement is down, friction force is up, so the work done by friction has to be negative. But to your surprise, the work done by friction comes out to be 0. Why 0? From the definition of work, we have learned that dw equals to f dot ds. Now tell me kids, what is ds? Sir, infinitely small displacement of point of application of force. At which point of this circular object does the friction force act? Sir, at the point of contact. If the body performs pure rolling, what is the velocity of the point of contact? If at any given instant this body has a velocity v and angular velocity omega, v has to be equals to omega. So at the point of contact, the velocity will be 0. So the infinitely small displacement of this point in an infinitely small frame of time will be 0. So ds will be 0. As ds will be 0, the infinitely small work done will be 0. So the work done by friction is 0. Why? Because there is no instantaneous displacement of the point of application of force. So the second case, if the surface has friction, then both the kinetic energy increases. Sir, which both? Translational as well as rotational. Now again you can use the concept of work energy. You will say work done by all the forces equals to change in kinetic energy. Work done by gravity plus work done by normal plus work done by friction equals to change in kinetic energy. So mgh, work done by gravity, plus work done by normal, which is 0, plus work done by friction, which is 0, equals to change in kinetic energy. Which kinetic energy? Both. Translational plus rotational. Translational kinetic energy is half mv square. Rotational kinetic energy is k square by r square times half mv square. So you can take half mv square common. So you get mgh equals to 1 plus k square by r square times half mv square. So beta cancel out bring the 2 up and divide with this quantity 1 plus k square by r square. So you get v equals to root 2gh upon 1 plus k square by r square under root. So that is the solution. So let's see more cases. So the question, here we have a solid sphere released from the top of an incline. We need to determine the speed of the solid sphere as it reaches the base. Question is, if the friction on the incline is sufficient to make the solid sphere roll, determine its speed on reaching the base. So what will be the speed of this solid sphere as it reaches the base of the incline? So you will say, again, here there is friction present and friction is sufficient that this solid sphere rolls. Work done by all the forces equals to change in kinetic energy. Which type of kinetic energy? Total kinetic energy, which means translational plus rotational. So you can say, as the solid sphere rolls down, work done by all the forces equals to change in kinetic energy. So work done by force of gravity plus work done by force of normal plus work done by force of friction equals to the change in kinetic energy, which is both translational as well as rotational. Since the body performs pure rolling, if at any instant it has a speed v, if the body has a translational kinetic energy half mv square, its rotational kinetic energy will be k square by r square times half mv square. So we will say the work done by gravity mgh plus work done by normal 0 plus work done by friction 0. Why is the work done by friction 0? Because the friction force acts at the point of contact, but there is no relative motion at the point of contact. Its instantaneous velocity is 0. Hence ds in the term dw equals to f dot ds, the term ds becomes 0. So the work done becomes 0. So work done by gravity plus work done by normal plus work done by friction equals to change in kinetic energy. Translational plus rotational, that is total, which is given by 1 plus k square by r square times half mv square. So from here we can calculate v. We can get v comes out to be equals to root 2gh upon 1 plus k square by r square. Since it is a solid sphere, the value of k square by r square will be 2 by 5. So substitute here 2 by 5. And what we get is root 2gh upon 1 plus 2 by 5. That becomes root 2gh upon 7 by 5 equals to root 10gh by 7. So that is root 2gh upon 1 plus 2 by 5. That is root 2gh upon 7 by 5. That is root 10gh by 7. Okay. Let's see the case when a body rolls on the incline. What is the friction force acting on it? What is its acceleration? So let's see that part. So body on incline, any circular body on the incline. So if a circular object is released on an incline, so we know that if this circular object performs pure rolling, it will have some acceleration as well as some angular acceleration. Now visualize the forces acting on this circular object. So there will be force of gravity, there will be force of friction, and there will be force of normal. So visualize these three forces. Question is, out of these three forces, which force provides the torque? So as the force of gravity and normal passes through the center of mass, they do not provide any torque. So who provides the torque? The force of friction. One can even break down the force of gravity into components. Along the incline and perpendicular to the incline. Since we know that in the direction perpendicular to incline there is no acceleration, the net force in the direction perpendicular to incline will be 0. Hence we can say the normal reaction will be equals to mg cos theta. The normal reaction will be equals to mg cos theta. And we can make the force equation for the acceleration down the incline. The net force down the incline equals to mass into acceleration. So mg sin theta minus f equals to mass into acceleration. This is the first case. Second equation we can make is the torque equation. Torque is provided by the force of friction. So this torque will be equals to friction force into R. So F into R, the torque, equals to I into alpha. And the last equation which we always make is the equation of no slipping. For the condition of no slipping, we can say that A has to be equals to alpha R. Substituting the value of alpha here, we can say that F into R equals to I into A by R, or the friction force acting equals to I A by R square, right? So F into R equals to I into A by R, or the friction force acting equals to I A by R square. This is okay. Now beta, if you substitute this friction force in the first equation, you will get that mg sin theta minus I A by R square equals to m. Bring this whole term to the right hand side and you write mg sin theta equals to m plus I by R square into A. And in place of I, you can write mk square. So substituting, you will write mg sin theta minus I A by R square equals to mm. Bringing this term to right hand side, you will get mg sin theta equals to mk square by R square. In place of I have written mk square by R square plus m times A. Now beta, cancel out m. So on the left hand side, you have got g sin theta, and on the right hand side, you have got k square by R square plus 1 into A. So the acceleration comes out to be g sin theta upon 1 plus k square by R square. Acceleration comes out to be g sin theta upon 1 plus k square by R square. So if they ask you for a ring rolling on an inclined surface, what will be the acceleration? So for a ring, you will substitute k square by R square as well. So you will get acceleration as g sin theta upon 1 plus 1, which is 2. If rather than ring, they give you solid sphere, what will be the acceleration of solid sphere down the incline? So you'll say for a solid sphere, acceleration will be g sin theta upon 1 plus 2 by 5. That becomes g sin theta upon 7 by 5. That will be 5g sin theta by 7. Right? So better keep this thing in mind. You must remember this particular formula. Moving on. Once you know that acceleration is g sin theta upon 1 plus k square by R square, substituting the value of this acceleration in the parent equation and solving, you will get that the friction force comes out to be equals to mg sin theta upon R square by k square plus 1. You need to remember this. So the acceleration will be g sin theta upon k square by R square plus 1. So in acceleration, you get k square by R square. In friction force, you get mg sin theta upon R square by k square plus 1. It's flip. Okay. We know that the value of k square by R square is maximum for ring. The value of R square by k square is minimum for ring. The value of k square by R square is minimum for a solid sphere, 0.4. And the value of R square by k square is maximum for solid sphere. So keep this thing in mind. Now in place of F, the friction force, you write mu n, and in place of n, you write mg cos theta. So you get mu mg cos theta equals to mg sin theta upon R square by k square plus 1. So to cancel out mg, bring this cos theta on the right hand side and divide. So you get sin theta by cos theta, which is tan theta. So mu comes out to be tan theta upon R square by k square plus 1. So this is mu minimum equals to tan theta upon R square by k square plus 1. So you need to remember these three results, I will say. If you remember these two, you will get the third one automatically, substituting friction force equals to mu mg cos theta. Okay, so let's move on and study some important points based on this. So now let's do important points. Let's say we have an inclined surface, and this inclined surface is frictionless. Frictionless means mu 0. And from the top of this inclined surface, we have released four bodies: a hollow sphere, a solid sphere, a solid cylinder, and a hollow cylinder. Sir, where is disk and ring? I am not talking about disk and ring because the moment of inertia of disk is same as that of solid cylinder, and the moment of inertia of ring is same as that of hollow cylinder. So they give us the same type of result. So that's why I'm not at all talking about them. Now, if all of them are released on the top of a frictionless surface, question is which one will reach the base first? So here students tend to answer wrong. Better stay focused. It's a frictionless surface. So there is no force of friction. There is only a component of force of gravity pulling them down. They will all do only translational motion, and the acceleration of all of them down the incline will be g sine theta. So all of them will move down with the same acceleration g sine theta. But if there is sufficient friction that all the bodies roll, then we have just learned that the acceleration will be g sine theta upon 1 plus k square by r square. Now for ring, the value of k square by r square is 1, ring and hollow cylinder. For disk, the value of k square by r square is half, that is 0.5. For hollow sphere, the value of k square by r square is 2 by 3, that can be taken as 0.66. And for a solid sphere, the value of k square by r square is 2 by 5, which is 0.4. Now you will say the lower the value of k square by r square, the lower the value of k square by r square, the higher will be the acceleration. So out of these four, which one has the lowest value of k square by r square? You will say it's a solid sphere. It has lowest value of k square by r square, hence it will have highest acceleration. And the acceleration of solid sphere will be highest, the acceleration of ring will be lowest. So remember that acceleration of solid sphere greater than acceleration of solid cylinder 0.5, after 0.4 you get 0.5, is greater than acceleration of hollow sphere 0.66, is greater than acceleration of hollow cylinder same as ring, which is 1. So remember this thing. Next thing, on which one of them the friction force acting will be highest? Sir, downward component is same for all of them, of force of gravity, mg sin theta. The one which has lowest acceleration will have highest friction force. Or you can think using the formula of friction force. We know that if the body performs pure rolling, the friction force has to be equals to mg sin theta upon r square by k square plus 1. So the one which has got lower value of r square by k square will have higher friction force. So the order has to be exact reverse. So the friction force on hollow cylinder has to be greater than the friction force on hollow sphere, has to be greater than the friction force on solid cylinder, and has to be greater than the friction force on solid sphere. So you need to remember these two things. Now, if all four of them are released on a surface where the friction coefficient is sufficient for them to roll, which one will reach the base first? So you will say, sir, solid sphere has highest acceleration. Since it has got lowest value of k square by r square, it has highest acceleration, it will reach the base first. So solid sphere will be the first to reach the base. Solid sphere will win this race. After reaching the base, which one will have maximum speed? So let's say any object comes down with an acceleration a and travels a distance l. We will say that the speed at the base has to be root 2al. The distance covered by all of them is same. 2 is same, so the one which comes down with greater acceleration will have greater speed after reaching the base. So solid sphere will reach the base with maximum speed. Solid sphere will reach the base with maximum speed. Now I ask you, out of these four objects, which one reached the base with maximum kinetic energy? Out of these four objects, which one reached the base with maximum kinetic energy? A student tend to answer solid sphere, which is wrong answer. All of them will have the same kinetic energy on reaching the base. Sir, why? See beta. Solid sphere will have highest speed. Yes. So solid sphere will have greatest translational kinetic energy. But understand that from the top till the bottom, if all of them do pure rolling, three forces are acting: force of gravity, force of normal, force of friction. The work done by normal and friction is 0. So only gravity is the one doing the work, and the work done by gravity on each one of them will be mgh. So the change in kinetic energy of each one of them will be mgh. When I am saying kinetic energy, it by default means total kinetic energy. I am not talking about translational kinetic energy. So if all have same mass, then all have the same total kinetic energy on reaching the base. All of them will have same total kinetic energy on reaching the base, and that total kinetic energy will be equals to mgh, work done by gravity. Now I ask you, which one will have highest translational kinetic energy? All of them will have same total kinetic energy, but since the solid sphere reaches with the greatest speed, it will have highest translational kinetic energy. So since the solid sphere has highest translational kinetic energy, it will have the least rotational kinetic energy, because the sum of both the type of kinetic energy is same for all the four bodies. So the one which has greater translational kinetic energy will have lesser rotational kinetic energy. So solid sphere will have minimum rotational kinetic energy on reaching the base. So with this, I finish off our entire mechanics part. See you guys in the next hour with the fun of heat and thermodynamics. The first topic we will discuss will be thermometry and linear expansion in the next hour. See you guys. Keep rocking. Bye. So that's all for now. See you guys in the next hour.